In this video, I will show you how to use Kmap, Carnograph map, and optimize some logic, and then use Xilinx IAC tool to actually build this logic that you optimized and put it on FPGA. Let's start with the design. So let's suppose we have 4-state FSM. Let's call it green state. This is start state, and as soon as you click the button, you go to the next state. As soon as you click the button, you go to the next state, either this pink or yellow. So in each state, this shape that shows the output value. So in this shape, it's called parallelogram. It's 1 is outputted on LEDs, for example, and on each state, this shape checks the input value. So if switches, this is connected to switches. So if switches hold value something and 1, then the output should be 0, 1 on LEDs, and on click of a button it should go to the yellow state. And in this state, if input switches does not equal to something and 1, then it directly goes to the pink state on the button click. And also before the button click, it outputs this value 1, 0 on LEDs. So note that this is a melee machine, because in this blue state, for example, or in pink or yellow state, as soon as you change the input value, it changes the output immediately before going to the next state. So without even going to the next state. So let's encode these 4 states. Let's call green state 0, 0, blue state 0, 1, pink state on the left 1, 0, and yellow state is 1, 1. Now, let's say we are in green state, and value of switches does not matter, because next state is directly the blue state. So here we fill a table. So if we are in 0, 0 state, doesn't matter the value of the switches. The next state is 0, 1, and output is 1, 1. LED is the output. Now from here, now we check this blue state. If we are in blue state called 0, 1, and input of the switches is something and 1, we go to the right, because it just goes to the right, and the output will be 0, 1 here. Output is 0, 1, and next state is yellow state, which is 1, 1. In the same state, if input is something 0, it goes to the pink state, that is here. Pink state is 1, 0, and the output is 1, 0. And same goes for the other states. So in each state, you describe each transition and outputs. Now, in order to optimize the circuit, before we optimize actually, now let's check how it actually works without optimization. So take a look of this on this line. When does the LED 0 gets 1? So LED 0 gets 1 in this case. Also LED 0 is the right part. LED 0 gets 1 also in this case, and this case, and this case. So these 4 cases can make LED 0 equal to 1. So what we do normally without Kmap is we say LED 0 equals to 0 0 something. So in this case it's um, 0 0 state, and doesn't matter what is the switch input value. Or the next description is 0 1 and something and 1, and the next case is 1 0 here. The current state should be 1 0, and something 0, and the last case is 1 0 something and 1. So normally we write this. So in this case, let's count how many 2 inputted gates are necessary to implement this logic. So here we need 1 gate, 2 and 3 gate, 4, 5, 6, 7, and then 8, 9, and 10. So 10 gates are necessary for this logic, and the levels of logic is 1, 2, 3, 4. 4 levels of logic. So if each gate delay is 1 nanosecond, the critical path is 4 nanoseconds, for example. Now, to optimize this with Kmap, we either do some calculations by ourselves, or we use this tool to do it instead of us. So here we do kind of same thing. We select here this. Let's interpret these 4 literal names as this. So W is current state 1. This is current state 1. X is current state 0. Y is switch 1, and Z is switch 0. Now here we select the cases I just highlighted here. So first case is 0 0 and something. So first 4 cases are all good for us. So this is first scenario. Actually, 1, 2, 3, 4. I have 5 literals. I need 4 literals. So this all cases are okay for us. Then we go to this option. This is 0 1 and something 1. So here, these 2, and then we select the later the next one. This is 1 0 1 0 and something 0. 1 0 and something 0. These 2, and the last one is 1 0 and something 1. So another here, and then we calculate. So we got this result here. Same, I had it here before. So that means instead of this logic, we can write this, and it will be all correct. In this case, we have 1 and 2 levels of logic and 2 gates. To make it easy for you, let's do this. I will just copy paste it here. Actually, I will just copy paste it somewhere here, and let's translate it into our language. So let 0 will be, in Kmap case, let 0 will be W, that is CR1 with inversion, and what is this? Let's make it 40. And Z is SW0, then OR, and not current current state, right? Yeah, current state 0. So naming is a little bit strange. So this is current state register. This is CR. Good. So here we got this. I want to put space. Good. And here we got current state 1, and I'm pretty sure Excel is not doing pretty well, or I'm not doing pretty well. So I'll just merge this. So here it will be current register 1 and current register 0, or okay, I have to put inversions here because I want them to be 0. So here then I do inversion of CR1 and current register 0, and this is switches 0. So I describe these two cases. Now the other two cases will be current register 1 and inversion of current register 0 and not again. So I can't freely click space. So inversion of current register 0 and the switches inversion of switches 0. This is third case, and the fourth case is current register 1 on current register inversion current register 0 and switches 0. Good. So instead of this, now I'm doing this. So first step would be to do this calculation on all output bits. So we have to do this. So I did this for LED 0, you have to do it for LED 1, and you also have to do it for next state 0 and next state 1. So we call this next state 1 and 0. And here I call it current state CR. I call it CR because it's current state register actually. So this is a register and this is not register, that's why I call it CR. So you have to do on all four output bits. You write these Boolean equations from Kmap, and then you have to construct it in Xilinx ISC. And also in Vivado and Altera. Yeah, and I was missing inversion here.